Did you know if we were to place a nucleus on one side of a balance and its separate nucleons on the other side of the balance, the separate nucleons would actually weigh more than the nucleus itself? How is that possible? To find out, stick around. We were talking about a difference in mass that will appear between the nucleus and its separate nucleons, which in physics is known as the mass defect. This bothered scientists for many years until Albert Einstein came up with his revolutionary hypothesis that energy and mass are actually interchangeable by the equation E is equal to mc squared, where E is energy, m is the mass defect, and c is the speed of light. So the energy equivalent to mass defect is known as the binding energy. The binding energy comes from the mass lost in the process of formation of the nucleus. Conversely, it is the energy that must be supplied to the nucleus to break it into its nucleons. One analogy to understand this concept better is to compare it with the electronic shell model. When an electron from a higher energy shell moves to a lower energy shell, energy is given out and therefore atomic mass decreases. Here the amount of energy given out is less, so change in mass is negligibly small. Similarly, if we apply this concept to the nucleus, when nucleons join together to form the nucleus, a huge amount of energy is given out comparatively, so decrease in mass is relatively more and is not negligible. We can now begin to see why some nuclei are more stable than others. The more the binding energy involved, the more stable the nucleus is. To compare the stability of different nuclides, we need to consider the binding energy per nucleon. This is found by dividing the binding energy of the nucleus, that is, the energy involved in the formation or breaking of the nucleus, by the number of nucleons in that nucleus. We can clearly see that iron has the greatest value of the binding energy per nucleon, so iron is the most stable element found in nature. The same binding energy graph can be used to explain nuclear fission and nuclear fusion. In fission, a heavy nucleus splits to form two lighter ones with release of energy, while in fusion, two lighter nuclei join to form a heavier one with a much more release of energy, as shown by the difference in the binding energy graph. That's why the hydrogen bomb is more destructive as compared to the atom bomb.